Okay, that's great. Thanks very much. Again, it's my pleasure to be here and talk a little bit about some of the work we've done on catalysis using these 2D materials. So let's get right into it. So the 2D materials that I'm referring to are these transition metal dichalcogenides, or TMDs, as George said. And just a very brief introduction to what TMDs are. There are these compounds with the chemical formula of MX2, where M is the transition metal, group 4 to group 10, and X is a chalcogen, so sulfur, selenium, or tellurium. And so you can combine these transition metals with the chalcogens to obtain different compounds, as shown here. And what's interesting is that these compounds have a wide range of different properties. They can be semiconducting, they can be metallic, they can be superconducting, magnetic, and so forth. So there's a whole sort of versatile chemistry that one can do just by combining the right sort of combinations of the transition metal with the chalcogen. In addition to the different combinations of the transition metal and chalcogens, one can also engineer their phases. So these TMD compounds occur in different crystallographic phases, and you can tune the different phases by doing chemistry. So you can achieve phase transformation at room temperature and pressure based on chemistry. The basic mechanism for achieving different phases is controlling the number of electrons in the d orbital of the transition metal. So these MX2 compounds, the electronic structure is determined by the d orbitals of the transition metal. The chalcogen orbitals lie deep within the gap, and so they don't influence the electronic structure, while the d orbital states lie closer to the Fermi level. And so if you take a compound like molybdenum disulfide, it has an even number of electrons in the d orbital. And so these compounds tend to be mostly semiconducting with a sizable band gap. But you can induce the metallic phase in MoS2 by adding an additional electron to the d orbital of the molybdenum. So for example, you could do that by doping. And so then you end up with odd number of electrons, similar to these D3 types of compounds. And these tend to be small band gap semiconductors or metals. So one can induce phase transformation in MoS2, for example, from the trigonal prismatic, which is the 2H phase, to the metallic octahedral, or the 1P phase. So in addition to the chemistry of tuning the transition metal and the chalcogen chemistry, one can also play around with phase transformation to obtain interesting properties in these compounds. So this is what the phases look like. The 2H phase in the case of MoS2 is shown here. The 2 refers to the fact that the unit cell in the case of multi-layered MoS2 requires 2 layers to define a single unit cell. But one can also have 1H phase configuration in a monolayer of MoS2. And the octahedral, or the 1P phase, is similar to the 2H phase, except for the fact that the sulfur atoms are slightly displaced. And so from the top, the 2H phase MoS2 looks like the typical hexagonal lattice that we're familiar with of graphite or single layer graphene. But of course, there is a sulfur atom at the top and at the bottom as well. So the monolayer of MoS2 is not a single atom thick, it's in fact 3 atoms thick. And when one compares the density of states between the 2H phase and the 1P phase, one can see that in the 1P phase configuration, there are finite density of states at the Fermi level, rendering this phase metallic. So the phase transformation in these TMD compounds is something that was discovered in the late 60s, early 70s, and quite a lot of interesting work was done by a chap called Robert Frint from Canada, and he's published many papers, including a paper entitled Single Layer MoS2 that was published in the mid 1980s. The chemistry that he developed is the chemistry that we utilize with some modifications for achieving phase transformation in these TMD compounds. And it's very simple chemistry. It involves taking the powder of these layered TMD compounds. So in the case of MoS2, the 2H phase, the trigonal prismatic phase, is a thermodynamically stable phase. And we simply put this MoS2 powder in a solution of butyl lithium. And so we have charge transfer from the butyl component of the butyl lithium, which is then stabilized by the counter lithium ion. And the charge transfer from the butyl part of butyl lithium introduces an additional electron in the d orbital of the transition metal, which then induces a phase transformation from the 2H to 1T. The additional charge on these sheets also render them soluble in aqueous solution in water and other solvents. And so we introduce this phase transformation, but we also do exfoliation because we have lithium intercalation during the butyl lithium process. And that intercalation expands the interlayer distance so much so that with mild sonication, we're able to create a uniform suspension of phase engineered metallic nanosheets of MoS2. So then we can simply take this solution and cast it onto the surface of a substrate, view it in SEM, in this case AFM, and we find these kinds of flakes of monolayer 1T phase MoS2 dispersed onto the substrate. One thing that I didn't mention is that once we've done the chemistry with the butyl lithium, we thoroughly wash away the organic component using hexane, and we also remove the lithium ions with water. We've done quite a lot of work using RBS and ERDA to confirm that both the lithium and the organic butyl lithium, butyl component of butyl lithium is removed. So what we end up with are these pure, chemically pure nanosheets of MoS2, except we started off with the 2H phase, but we end up with the metallic 1T phase. And these metallic phase of MoS2 are characterized by these J1 and J2 peaks in the Raman spectrum. And one can also work out the fraction of the 1T phase in the phase engineered samples by doing XPS. So yeah, so we can end up with up to 80% 1T phase in a nanosheet of MoS2. But we can also look at these monolayers in under high resolution scanning transmission electron microscopy, and at very high concentration of the metallic 1T phase, we end up with these Jahn-Teller distortions, which leads to clustering of the appearance of this clustering effects, and this is classified as the distorted 1T phase or the 1T prime phase. So it's another sort of crystallographic phase of these TMD compounds. In this case, this is for tungsten disulfide, and this introduces quite a large amount of strain onto the nanosheet. So there's local strain. There's these bright regions, which are sort of high strain regions, and dark regions, which are low strain regions. So it's not uniformly on the sheet as a whole. The sheet itself is not strained. It's in equilibrium, but locally you have high amount of tensile and compressive strain. So of course, we know that strain influences not only the thermodynamics of a catalysis reaction, but also the electronic structure. So, so this ability to control the concentration of the 1T phase by controlling the butyl lithium chemistry allows us to tune the strain in these materials as well. So we have these sort of multiple variables, multiple knobs that we can tune to achieve the properties that we want. Of course, the 2H phase, which is a thermodynamically stable phase, is strain free. So that sort of gives you a background of I'll just admit this person. the background of TMD materials and some of the phase engineering work that we've been doing over the last decade or so. So now let me shift to catalysis for the hydrogen evolution reaction. And so there was a lot of interest or there is a lot of interest in using these materials as electrocatalysts. But using MoS2 for the HER reaction was really, the interest in this was really sparked by the original work of Thomas Jaramillo at Stanford, who showed that the edges, the metallic edges of these MoS2 clusters grown on gold were active for the hydrogen evolution reaction. And so that led to quite a few researchers and groups around the world trying to increase the concentration of edges to really improve the HER performance of MoS2 by making these types of fractal structures and others, other types of mesoporous structures. So in addition to increasing the concentration of exposed edges, there's also work being done to find more efficient pathways to allow the electrons to reach the active sites. So we know that the edges are metallic, but the rest of the flake is a semiconductor or even an insulator relative to the edges. And so you need to have you need to create pathways for the electrons that are injected from the support to go to the edges where catalytic reaction can occur. And of course, strain has a large influence on the thermodynamics. So strain tuning has been explored in these materials for improving the catalytic performance. I'll talk about the utilization of the metallic phase of these TMD compounds. This was something that was pioneered in my group very early on for HER reactions. And then also there's a lot of interest in coupling. When you look at sort of non-metal catalysts or metallic catalysts, then the coupling with the substrate becomes quite important, because if you have a semiconducting catalyst, as in the case of MoS2 here, then there is a junction between the substrate and the catalyst, and that has to be taken into account. So we've been studying coupling of the catalyst with the substrate using these microelectrochemical cells since the last 5 or 6 years. And the active sites in these MoS2 catalysts is in fact defects, specifically sulfur vacancy. So we've been studying the role of defects on TMDs for HER. So I'll talk about some aspects of this work. But our sort of basic approach to electrocatalysis, so it has been to leverage our background in electronics and electrical engineering to really understand each step of the catalytic reaction. So our approach has been to break up the process, the HER process, in 3 different steps. The first being electron injection from the support to the catalyst. So this, for us, from an electrical engineering point of view, is basically contact resistance. In catalysis, we refer to as charge transfer resistance, but there's a barrier between the MoS2 and the glassy carbon support in this case, and in order for the electron to be injected into the catalyst, it must overcome this contact resistance barrier. And obviously, we'd like the barrier to be as close to a 0 EV or negligibly small as possible. But we can probe this and optimize this, and I'll show you how we've done that. And the second thing is that we need to transport the electron to some active site. If it's a sulfur vacancy, then the electron that's injected, it has to be transported there. And so one can imagine that electron transport is facilitated in metallic materials, and it's a bit more cumbersome in semiconducting materials. So by really making these TMD compounds metallic, we can facilitate the electron transport to the active site. Then the third step, of course, is once the electrons reach the active site, it must react with, combine with the proton. And that's driven, of course, by thermodynamics. And I'll show you how we can tune the thermodynamics by tuning the strain in the material. So we've been studying over the last 10 years or so all of these different processes using an idealized system of these atomically thin TMD materials. Okay, so the first thing is that what we find is that when we test the metallic phase of MoS2 compared to the semiconducting phase of MoS2, that is the 2H phase of MoS2, what we find is that we have substantially better performance in terms of the overpotential decrease and also the current density. We can also, as I'm sure everyone's familiar, replot the same data over potential as a function of the current density to obtain these linear curves from which we can extract the Tefl slope, which tells us about the limiting reactions that occur in different catalysis systems. And what we find here is that the Tefl slope is quite good for this 1T phase MoS2, and the overpotentials are also reasonable for these metallic phase relative to the 2H phase of MoS2. So this could be for two reasons that I mentioned in the previous slide. One could be that the junction between metallic nanosheets of MoS2 and the glassy carbon is a low barrier junction, so charge electron injection into the catalyst is facilitated. And then, of course, the 1T phase is metallic, so electron transport could also be facilitated in the metallic phase. Okay, and so one can then plot the catalytic activity in terms of the exchange current density as a function of the 1T phase concentration, and one can see that there's a direct correlation between the activity of the catalyst and the concentration of the 1T phase. So one can see that one can increase the catalytic activity from the purely 2H phase to the 1T phase by almost an order of magnitude. That is, the current density increases by a factor of 10 when we go from the semiconducting phase to the metallic phase. So then we wanted to probe this influence of the contact resistance, that is the charge injection, and the whether that's a bottleneck or not in catalysis. In order to test that, we devised these microelectrochemical cells in which we make essentially a three probe system, where we have our counter electrode, our reference electrode, and our working electrode, but all within this sort of lithographically patterned device. And the reason why we wanted to do this is because early on there were a lot of questions on whether the edges were catalytically active, was the basal plane completely inactive of MoS2, and whether the 1T phase was really catalytically active, or were we just measuring the edges. And so these microelectrochemical cells allow you to really probe all of the different aspects of our MoS2. So in this image here, you might be able to make out these dark triangles in the background. And what these dark triangles are CVD grown MoS2, they're monolayers. And on these CVD grown MoS2, we've patterned these electrodes using standard lithography. But the way we've made this device is that the only part that is exposed here is this blue region. The gold electrodes and everything else is covered by an insulator. Everything, of course, the gold electrodes are contacted to MoS2, but the only thing that is exposed here is this blue region of the MoS2. So then we can put a droplet of our electrolyte, as shown in this photograph here, on top of this, and the activity, any catalytic activity that occurs only occurs from this blue region, right? So we can neglect the influence of gold or anything else. What this allows us to do is to have a very specific area over which the catalytic activity occurs. So in this case, what we've done is we've exposed the basal plane of MoS2. The edges are completely covered. They don't participate in the catalytic activity. In this device, we've covered the entire basal plane and only exposed the edges of the MoS2. So now we can probe the activity just from the edges or just from the basal plane. In addition, we can also phase transform this basal, so we can measure the activity of the 2H phase. We can do the phase transformation to convert it to the 1T phase and measure the catalytic activity again. In this way, we can compare whether it's the metallic phase that's active, whether it's the 2H phase that's active, or whether the activity is coming or whether the activity is coming from only the edges. Sorry, my house phone is going off. Yeah. And so we've made devices in which we've tuned the contact resistance. So depending on the metals that we utilize, we can tune the contact resistance between the semiconducting or the metallic MoS2 and the electrical contacts. And so then we can measure the polarization activity of the reaction as a function of the contact resistance. And it's not surprising that the device with the lowest contact resistance gives us the best electrocatalytic performance. But this is sort of although it confirms what might seem to be obvious, it's a sort of a way for us to quantify the degree of the influence of contact resistance on the catalytic activity. And so this really led us to devise better supports to improve the HDR performance of our catalyst. And so we as in a different project in our group, we devised a method to efficiently reduce a material called graphene oxide to achieve very high quality carbon supports. The reduction is done by microwave irradiation with microwaves. But what we found was that when we put our catalyst on these microwave reduced graphene oxide, we get substantially better performance, HER performance, in terms of the overpotential and also the Tefl slope. But we also get much better stability of our catalyst on these supports. So really the fundamental work with contact resistance led us to devise a much better support, which not only gives us better electrocatalytic performance, but also increases the stability of the catalyst. So in the sort of the last part of my my talk, I'm just going to talk about some ways that we've been trying to tune the thermodynamics of the HER process on these TMD catalysts. So one thing that we wanted to probe a little bit deeper was to really understand where the catalytic activity in these TMD compounds was coming from. So of course the pioneering work by Jaramillo showed very nicely that it was the metallic edges that were catalytically active, and then some of the work from my group showed that the metallic 1T phase was essential in improving the catalytic performance, even when we didn't take care to expose the concentration of edges. We got activity from the basal plane as long as they were in the metallic phase. And then, of course, there was a lot of work done on pointing out that it's most likely the sulfur vacancies that were catalytically active. And so we wanted to probe this a little bit deeper. So what you're seeing here is a high resolution TM image of a single layer MoS2 film and these orange circles indicate the presence of or the absence of a sulfur atom, that is a sulfur vacancy. And these yellow circles represent where both the sulfur atoms, the top and the bottom sulfur atoms, are in fact missing. So there's one can introduce quite a large number of sulfur vacancies in MoS2, and the MoS2 still remains stable. So there's the concentration of sulfur vacancy here is 9%, and yet this monolayer MoS2 still behaves like MoS2 when in terms of the optical properties and electronic properties. So I find that remarkable. But that's a different talk. And so what we wanted to do was to rationally introduce different concentration of sulfur vacancies and measure the HER performance of these different samples with different sulfur vacancies. And so the way we introduce different concentration of sulfur vacancies is that we grow our MoS2 by chemical vapor deposition. So these are monolayers. And then we irradiate these samples using a helium-ion beam at different dosages, as indicated in the TM micrographs. And the good thing about the helium-ion beam, say compared to an argon-ion beam, is that the helium-ion beam is quite gentle in the sense that it's able to remove sulfur atoms without destroying the entire structure. That is, we can remove the sulfur atoms one by one by radiating with a helium-ion beam while maintaining the overall MoS2 or the nanosheet structure. And until you go to very high dosages where you can clearly see that we've introduced structural defects at dosages of 1 × 10⁻15 helium ions per centimeter squared. But at these sort of concentrations, we're able to remove the sulfur vacancies without disturbing the structure dramatically. And so there's a direct correlation between the vacancy concentration as a function of the helium ion dose. And then we utilize our microelectrochemical cells to make measurements on these samples with different vacancy concentrations. And one can see that the general trend is that as you introduce more sulfur vacancies, you get an enhancement in the catalytic performance until you get to the point where you start introducing structural damage. When you start introducing structural damage, you disturb the contact, you increase the contact resistance, and you also decrease the electronic transport. And so, but there's a sort of an ideal vacancy concentration of around 5.7 × 10⁻14, where we get the best catalytic performance with good Tefl slopes. And so we wanted to probe this, a bit more. So we also calculated the turnover frequency, and what we find is that at this concentration, at this magic concentration of 5.7 × 10⁻14, there is a dramatic increase in the turnover frequency of the active site. One sort of a very back of the envelope calculation that one can do is, because we are measuring the HER the current density in terms of milliamps per centimeter squared, and we know the vacancies per centimeter squared as well, one can in principle calculate the activity of a single atomic vacancy, or the current due to the atomic vacancy. Of course, there's a lot of assumptions there, but it's sort of a nice way to get an idea of what the activity of a single vacancy is. But we were sort of curious about what's causing this magical, what's happening at this sort of magical concentration, vacancy concentration. And so we did some transport measurements and also spectroscopy and various other things. And what we found is that with the Raman is that the Raman looks reasonably okay, but at this sort of concentration where we get good catalytic performance, the intensities sort of change and the peaks tend to be broader, but it's still essentially the MoS2 spectrum. And in the case of the electronic transport, this is basically a drain current of a field effect transistor as a function of the applied gate bias. It tells us about the electronic properties of the material. And I won't go into the details, but for those that are familiar with the FET measurements will recognize that when we have just pristine MoS2, we get nice semiconducting behavior. That is, we're able to modulate the current, the electronic current, as a function of the gate bias. But when we go to this vacancy concentration, we see that we get a flat uniform current. That is, there's no modulation of the device current, the drain current, as a function of the gate voltage. And this is a characteristic of a metal. So by introducing a sufficient amount of vacancies, we've actually, the material's undergone a phase transformation, perhaps not structural phase transformation, but electronically it's gone from a semiconductor to a metal. And so this is similar to what we see with the 1T phase, where the metallic 1T phase is a better catalyst than the semiconducting 2H phase. So by introducing the right amount of vacancies in sulfur vacancies in the sample, we're able to achieve good catalytic performance. So in addition to this phase transformation from semiconductor to metal, we also imaged our material close to these vacancies. And what we find is that locally, there's a substantial amount of strain that is present. So if one looks at this dashed red line, one can see the dashed red line is horizontal, it's perfectly horizontal, but one can see that the atomic plane deviates quite dramatically from the red dashed line. And same here. So it suggests that there's sort of atomic movement, and we can do this kind of mapping to show that locally there is a strain of approximately 3% in the material. And so there's been a lot of work done by our group and also the group from Stanford on studying the thermodynamics of the HER on MoS2 and other TMDs with strain. And so one can see that when you have a certain amount of strain and certain amount of vacancies present in MoS2, one can achieve thermoneutral conditions for the HER reaction. And so I showed you from one of the previous slides that we have a vacancy concentration of around 9 to 10% and a strain of 2 to 3%. And so we're in this sort of category of delta G, which is close to 0. And our own sort of calculations from 2013 showed that when you have a highly conducting TMD compound with sufficient amount of sulfur vacancies and also strain of around 2 to 3%, one can achieve this thermoneutral condition for HER. In HER, of course, we want thermoneutral condition for the delta G to be close to 0 because we want to have the proton adsorb onto the active site and the hydrogen to desorb from the catalyst as well. So that's the ideal condition. So the role of strain is quite important in determining the thermodynamics. So we can control by tuning we can tune the strain in 2 ways. One, by introducing sulfur vacancies, and 2, by tuning the concentration of the metallic with the 1T phase. And so we took all of this knowledge, and in 2017 we wanted to design a catalyst that would give us good catalytic performance and also be practical. So we started looking at these niobium disulfide catalysts because niobium disulfide is naturally metallic, highly conducting. Niobium is a good catalyst for HER, and we were able to make these niobium disulfide catalysts using our CVD process directly onto glassy carbon. And we fabricated these crude electrolyzers and demonstrated that we're able to achieve current density values that are quite large, hundreds of milliamps or even 1 amp per centimeter squared. So with that, let me conclude by just acknowledging the people who've worked on catalysis with TMD compounds in my group. So the whole sort of work on looking at the TMDs for HER was started by Damien Vorey. We were primarily optical and electronics group, but Damien joined my group in 2012. He's one of the best inorganic chemists that I've ever met, and he started the work on utilizing these metallic phases for HER and other catalysis, and now he's continuing that work in Montpellier. Jun Yang was my postdoc who followed Damien and has continued the work, and some of my other collaborators and students that have also contributed to this project are shown here. So with that, I'd like to thank you for your attention, and I'm happy to take any questions that you may have.